Hi, I'm Les Kirkup. Welcome to this introductory video on experimental methods in science and engineering. If you're studying a course in science and engineering, it's highly likely you'll be required to carry out experiments, perhaps as part of a lab program or a lab-based project. To help you in your studies, this and other videos will explore the practices and methods that scientists and engineers apply when they do experiments, and which are applicable when you yourself do experiments. A good place to start is to ask the question, why do we do experiments? What is their purpose and what is their value? A famous scientist once said the following: the principle of science, the definition almost is the following: the test of all knowledge is experiment. Experiment is the sole judge of scientific truth. That scientist was Richard Feynman. He won the Nobel Prize in the early 1960s for his work on quantum electrodynamics. Feynman was a theoretical physicist. He didn't do experiments, but he understood that unless his theories were supported by reproducible experimental evidence, his theories would not be wholly accepted by the scientific community. I'd like to illustrate the importance of experiments with a particular example. Here we see Albert Einstein, perhaps the most famous scientist of the 20th century. Einstein's theory of general relativity was published in 1915. The theory predicts many interesting things, one of which is that the path along which light travels is bent by the gravity associated with a massive object. The theory of gravitation due to Isaac Newton also predicts that the path that light takes would be bent by the gravity of a massive object. However, Einstein's theory indicates that the bending would be twice that predicted by Newton. Einstein was a theoretical physicist. He didn't have the skills or resources to do an experiment to test his theory. It was necessary to wait for someone who did have those skills and resources to carry out such an experiment. Enter this person. This is Arthur Eddington. He was an astronomer. In 1919, he and a group of scientists set about investigating the bending of light by a massive object. That object was our sun. When the sun is visible, it is impossible to determine whether light, as it travels, say from a distant star, is bent by the action of the sun's gravity. Eddington had to wait until the light from the sun reaching the earth was blocked through a total eclipse before he was able to measure the deflection of light from a distant star. Here is one of the images of the eclipse that Eddington obtained in 1919. If you look closely, you will see a few dots which are the result of light from stars striking Eddington's photographic plate. Here you see highlighted a couple of the stars. The question is, has the path that the light took been bent through interaction with the sun's gravity? Let's look at this in a bit more detail. Here is a star, and here is our sun. Some of the light from the star will pass close to our sun. If it's undeflected by the sun's gravity, it'll travel in a straight line. Einstein predicts that the light would be deflected by the sun, so let's show that, and we'll exaggerate the angle to make the diagram clearer. Let's make the angle between the undeflected path of light and that deflected by the sun d. Einstein predicted that d, which we'll write as d subscript e for Einstein, is 1.75 arcseconds. This double prime is a symbol we use for arcsecond. Newton predicted a value exactly half of this, so we'll write that as d subscript n for Newton, 0.875 arcseconds. The experimental value that Eddington obtained was 1.6 arcseconds. But in fact, he got a little bit more out of his data. He found an uncertainty in this value of 1.6 arcseconds, which we'll write as follows. The experimental value is 1.6 plus or minus 0.3 arcseconds. This 0.3 is the uncertainty in the 1.6 arcseconds. We can write this another way. We can subtract the 0.3 from 1.6 to get the minimum, which is 1.3 arcseconds, and the maximum that the deflection could be experimentally is 0.3 plus 1.6, which is 1.9 arcseconds. Now if we look at the predictions of Einstein and Newton, we see that Einstein's value of 1.75 lies in this interval of 1.3 to 1.9 arcseconds. By contrast, Newton's does not. This was powerful evidence for the superiority of Einstein's theory. On the publication of Eddington's findings, Einstein became almost instantly famous. He was already known in the scientific community, but this experimentally founded vindication of his theory made him an international celebrity. Since 1919, there have been many other experiments that have tested Einstein's theory of general relativity. To date, there are no known exceptions to his theory, and that theory remains the best we have to explain gravitation and its effects. Few experiments are as influential as that of Eddington's. However, all experiments have something to teach us. Experiments begin with a question. For example, does the efficiency of a solar cell depend on its temperature? And if so, in what way? The challenge is to devise experiments to answer these and similar questions, and to report what we found to others. In subsequent videos, we'll consider gathering, presenting, and analysing data, and what you must do to report what you found to others. Until then, goodbye for now.